So this is Griffiths Electrodynamics, problem 5.1. So we're looking at a particle of charge Q, and it's going to be entering this region right here that has a uniform magnetic field B. Okay, so B is in this region here, and it's uniform, and it's pointing into the page. The field deflects the particle a distance d, so this little distance here, above the original line of flight. So the original line of flight is right through here, and as it exits the region of the field, it's displaced a distance d above where it would have been without the field. Is the charge positive or negative? And in terms of A, D, B, and Q, find the momentum of the particle. Okay, so first, just using the right-hand rule, let's just decide whether this charge is going to be positive or negative. So if we use our fingers here as the field lines and our thumb as the velocity, if it's positive, it will obey the right-hand rule. If it's negative, then it will be the opposite. So I guess you could say it obeys a left-hand rule. Okay, so if I point my fingers towards the page, so in the same direction as the magnetic field, and my thumb is in the direction of the velocity, then my hand is pushing upward. So there would be a deflection upward. All right, so since this deflection is in this direction, it is obeying the right-hand rule, and we can say that this charge here is positive. Okay, so now we're going to look at the momentum of the particle. So for this, we'll just turn straight to Newton. The only force on this particle is Lorentz force. So electric field plus V cross B. All right, there is no electric field in this problem, so that part will go away for us. And inside this region of the field here, we're going to be following circular motion, so cyclotron motion. There's a formula in the book for that we can look up and save some time, but we'll just derive it real quick. Okay, so looking in here, just in this region, right, where we're only looking at this curved path, which is just an arc, a segment of a circle. And for uniform circular motion, the acceleration is equal to, it'll be minus v squared over, I'll use big R for the radius. So imagine if we were to look at the center of this arc, the radius, where would that be? So the center would be around here, and so the radius would be, the distance to that point if we were to draw the complete circle. Okay, all right, and then this is in the r hat direction. Okay, so maybe in a different color, I'll just kind of draw this out a little bit. So if this is the center, I'm just drawing this radius to this this curved segment of the path. Okay. All right. So the acceleration has to be pointing towards this center to get this circular path. All right. And now, if we're going in this direction, we're going to say that the velocity of this particle is just equal to v, and it's going to be in the phi hat direction. Okay, and if we're calling phi positive, meaning going like if this direction is positive, then our z-axis in this so to have a right-handed cylindrical coordinate system, our z-axis would need to be pointing up. The B field is pointing down, so our B field is negative B, and then z hat direction like this. Okay, so now we'll just use our good old Newton's laws, right? So RF to MA. All right. So what we have here is a Q multiplied by a V cross B. Okay, that came from just right up here without the E, right? So it's just a magnetic force is equal to MAC, except for AC, we're putting in this minus V squared over big R hat. All right, so let's go ahead and plug in some of our, so for V and B, right? I'm just going to bring the constants out front, so we'll have a minus sign from right here, and then we'll have a V and a B. And then we're going to have a phi hat crossed with a z hat for our vector part. Okay, just right here. All right, and then this is just on looking at this side again, so minus mv squared over big R, and now we have our r hat. All right, so while these minus signs can go away real quick, let's look at our vector part real quick. So the phi hat direction we decided was going this way, sweeping around this arc, right? So if we look at just a little piece of it, right, let's just say right at this point where this green line hits this line, it's going like this, okay? Phi hat crossed with z hat. So by the right hand rule, so phi hat's going this way, z hat was going up, and so our result will be pointing outward from this point, which is the r hat direction. All right, so you can see here's the r hat. So this phi hat cross z hat is equal to r hat. All right, so we'll just since these r hat vectors are the same on each side, we can just equate the magnitudes here. So, and I'm also going to take out one of these v's. All right, so we have a qb equals mv over r. All right, let's just check this real quick. If you look at equation 5.3 in the book, qb, anyway, basically with our momentum right here, right, which we'll call P, we get that as QBR. All right, and so this agrees with what's in the book, so we're on the right track so far. All right, so now we just need to find what P is, and we need to put it in terms of our four original variables. We have the Q, we have the B, we just have to put it in terms of A and D. So we just have to find R in terms of A and D, and then we'll be done. So we'll just use the formula for a circle. So let's redraw this real quick. Center point is out here somewhere, right? I didn't draw that arc very well, but all right. So here's an R. Okay. All right. So here's our circle, and we just need to find R in terms of these two. So let's see. Our equation for a circle is just x squared. Well, yeah. Let's just leave this as x squared because our center will be, if this is the x-axis and this is the y-axis, the center of our circle is at x equals 0, okay? Y minus the y coordinate of the center, right, squared, all right? Normally this would be just like this, but x sub c is equal to 0, so that's why it doesn't appear there. And that's equal to r squared, okay. So, this x and this y will fit on this line, and So what we have, if we just pick this point here at A and D, D is our y and A is our x, so we have an A squared plus D minus, alright, so y sub c, that's the y component of the location of our, the center of our circle, which is at x equals 0, y equals big R right here. So y sub c is equal to big R squared, okay, and that's equal to R squared. So now we're just going to solve this for R. So we have A squared plus D squared minus 2DR plus R squared equals R squared. All right, these are going to go away. We'll just pull a little trick here and call this an equal sign, right? So all we did was add both, add 2dr to both sides. And now what we can see is that solving for r, what we've got is big R equals A squared plus D squared divided by 2D. Alright, so what we have to do now is just plug this into our formula for the momentum, and we're done. So we have Q, B, and then we just have to plug in this R. So an A squared plus D squared divided by 2D. And so there we have it. That's the momentum in terms of these four quantities.